lots of clues in every problem, you should be able to figure out whether they're looking for an exhaustive search algorithm or not looking for an exhaustive search algorithm. And it turns out you can easily figure this out. Say, for instance, there is some problem where you have to try every possible binary number. Okay? If you have to try every possible binary number, we know that there are 2 to the n different binary numbers of length n. Now, what kind of values of n would be reasonable? What do you think?
20.
So 10 should be easy because 2 to the 10 is about 1,000, right? 2 to the 20 is 1,000 times 1,000. That's about 1,000,000. Should be no problem. 2 to the 30 is getting borderline. That's about 1,000,000,000. Maybe hard to say. If you have lots of work to do in each iteration, then maybe not. But if you're just trying to print out binary numbers, maybe somewhere up to there. So somewhere between 20 and 30, you're going to hit a ceiling, right? So if your n is somewhere around there, then there's a good clue that you're expected to write some kind of an exhaustive search code. Okay. But again, you have to be a little bit more careful. You have to check out all the parameters that are needed in order to figure out the time complexity. If it's only one value of n, then even if it's an exponential time algorithm, 2 to the n, you can still handle this for about 20, maybe even up to 25 or so. Okay? All right. Then if you're doing permutations, the time complexity is, or the number of permutations you get is how many?
Factorial.
It's factorial. It's n factorial. Now, what kind of values of n are feasible in order to try every possible n factorial permutations? So here you have to be even more conservative than 2 to the n, right? 8, 9, 10, maybe. You don't think even 10 would work?
I think it's 300,000 for 9.
Yeah.
360.
Yeah.
So
10 would be about 3 million then, right?
3 million. If you're just doing 3 million, that's fine.
Yeah.
But
if you're going to do additional work within each iteration, then it becomes too much. So you will know again. So if the number looks like a single-digit number, then again, it's very good chance that they are trying to get you to do exhaustive search of some kind, possibly listing out all permutations. So these are all things to watch out for. Even if it is n choose k, and n is, let's say, around 20, k actually can be anything you like, and it'll still be within bounds that are reasonable. Sometimes in each of the iterations you have to do additional work. There may be some other variable, and if that happens, so it might be n choose k times some other m, okay? Or maybe you have to do this for 10 different data sets, or you have to repeat it for, I don't know, 10 different classes or something like this. Well, then the number of the n that you can try will become even smaller, right? So you have to be careful about all of this if you want to know what is feasible and what's not. So look at the numbers that they want. Think about the time complexity of the algorithms you're going to use, and then based on that, figure out what things to completely rule out. Okay? Because that will help you to say, oh yeah, forget it. This combinatorics thing is not going to work out. Combinations, forget it. It's not possible. If n is 100, you know immediately that you're not going to do any kind of it's unlikely you'll do exhaustive search of some kind. But that's only if 100 is part of the parameter that's going to show up in the exponent. By the way, n factorial also is an exponential value. It rises as fast as 2 to the n. It actually is larger, typically larger than 2 to the n, but it is considered an exponential quantity. So anything that looks like either 2 to the n or looks like n factorial, it's going to be a problem with any algorithm where the value of n is too large. So these are all good clues to think about. If you are thinking of trying some exhaustive search and n looks like 1,000, you know you're on the wrong track. So these are all clues to pay attention to. Is that fine? Questions? Okay, now with most graph algorithms, you're going to get algorithms that are either linear, quadratic, or cubic. And we'll see at least the names of the algorithms and what they do and what are the time complexities. If you have a linear time algorithm, you can safely work with values of n that go up to, I don't know, 10,000, 100,000, maybe even 1 million. With a quadratic algorithm, you shouldn't be thinking about anything where n is bigger than, let's say, 10,000. Okay, because you're hitting some boundaries very, very quickly. If n is 10 to the 4, n squared is 10 to the 8, and well, you're getting dangerously close to something that's not going to finish quickly enough. If it's a cubic algorithm, well, what kind of values of n should you expect? Somewhere in the 100 range. 1,000 is already too much. Okay, so 100, 200 is okay. Anything beyond that, you're starting to hit some dangerous boundaries. So all of these again are clues for you, because most likely they have thought about this and made the numbers as high as they can because they want to make sure that you're writing efficient algorithms. So one of the things that you'll see with many of these competition problems, there are some problems where where an obvious, naive solution is very, very easy. You should be able to just figure it out just by looking at it. But in such case, it's possible that those naive solutions are not fast enough. And you can quickly test this using the things that I just told you. Check whether it's a linear, quadratic, or cubic, and check what the values of n are, and figure out whether the naive algorithm is going to work or not. If it doesn't work, then again, you can look at those numbers to figure out some clues. Okay, we talked about n squared algorithms where you shouldn't go more than 1,000, maybe 10,000 or so. What about an n log n algorithm? Well, with an n log n algorithm, you can actually go a little bit more. Maybe 10,000 is actually still fairly safe, right? Maybe a little bit higher as well. So you will know what kind of limits to have in mind in order to design these algorithms. And that kind of quick analysis you should be able to do even with the mock competition problems. Okay. Because the problems typically, at least on the mock competition, are relatively easy, and we should at least put one problem where the naive algorithm is easy, but the efficient algorithm requires something that for them to know. Let's say, one of the standard algorithms. So if you're doing a sorting, okay, again we know that there are lots of n squared algorithms, your bubble sort, your quick sort, blah, blah, blah. But then there are very few efficient sorting algorithms. And depending on the value of n, you will know whether it's critical to use an efficient sorting or not, right? So again, these are things to pay attention to. So even a simple step somewhere in your algorithm where you're just saying, oh yeah, first sort this before doing blah, 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 is not going to work out unless the value of n is somewhat manageable. Okay? All right, so let's talk about graph algorithms. So do you think there are people on Zoom? Should I zoom in?
If you put it out, I'll put it out. But
Yeah.
usually we get 1 or 2 people on there.
Yeah.
And I am recording it.
Okay.
People can watch there.
All right. Okay, then I will not do that. So what kind of graph algorithms are things that we learn in the data structures class? Well, the first thing before you talk about problems or algorithms is, what is a graph? What are the definitions? So quickly, definitions are that G is a graph. It's defined by a vertex set and an edge set, right? And it's instead of trying to define it, it's just easier to visualize one. So you have a bunch of vertices, and you have some edges connecting them. This is a graph where the vertices are the endpoints and the edges are connecting these endpoints, right? So in this case, it turns out that there are 3, 3, 6, 3, 9, 1, 10 vertices, and I don't know, some dozen or so edges here, right? There are actually 2 kinds of graphs. One is a undirected graph or a directed graph. If this here is an example of an undirected graph where between any 2 vertices there is an edge, but the edge does not have a direction. You could provide directions for these edges. Okay. Here we are providing directions for each of the edges. This is an example of a directed graph. You could also have graphs that are weighted or unweighted. Then within the weighted graph, well, this here is an example of an unweighted graph. In a weighted graph, each of the edges has a certain weight. So it could be 2, 3, 4, 7, 19, 11, 2, 6, 5, 4. You could even have negative numbers, theoretically. Okay? So in terms of the weighted graphs, there are 2 kinds of weighted graphs. You could have weights on vertices or weights on edges. We'll call that edge weighted. Whatever I've shown here is an example of an edge weighted graph, but in reality you could also have weights on the vertices. Each of these is meant to model a different situation or a different problem. Okay. All right, so these are all standard definitions. Then there are definitions related to paths and reachability and connectivity and blah blah blah. So the field is very, very large. There's no way for me to cover everything, but for instance, if there is a directed graph like this, then this here is an example of a path. So this is a path that starts here and ends here, right? And in this case, it's actually a directed path because the edges are directed. There's also a concept of cycles. And you could either have undirected cycles or directed cycles. In this particular case, you have a cycle over here. That, and that. Right? So there's a concept of paths and cycles. There's a concept of reachability. So over here, I can I can reach this vertex starting from this vertex. So that's the reachability concept. If it's not a directed graph, then it's a lot easier to talk about reachability. If there is some path from this to this, then it's reachable. Okay. So reachability is also related to another concept called connectivity. A graph is called connected if every pair of vertices is reachable. Okay. In this case, in this directed graph, it's not exactly reachable because I can go from here to here, but I cannot go from here to here. Right? I can't make it backwards. But if it's an undirected graph, then it's a lot easier to think about this. If I remove all the directions for the edges, then this whole graph is connected because everything is reachable from everything else. Right? So connectivity is an important concept. Then we have the concept of a subgraph and the concept of a tree. A subgraph is any piece of this graph. So for instance, if this is the graph, then a subgraph of this graph could be some other graph where the vertex set is a subset of the vertices here, and the edge set is a subset of the edges here. Okay, so this is the concept of a subgraph. And in a subgraph, V prime is a subset of V, E prime is a subset of E. When this happens, you say that G prime is a subgraph of G. Then there is a concept of a tree. A tree is a subgraph that does not have cycles. Okay? So you could take some of the edges here, you could take some of the vertices here, and whatever you get, if it's a so I may have misspoken here. A tree is a connected subgraph without a cycle. Okay, so in this particular example, I could have that, and I need one more. Okay. So I've only taken some of the vertices here, so let me just label the vertices. Hij. So I would have A, B, C. Okay. So that graph here is a subgraph of this graph. It's connected because everything is reachable from everything else. And it has no cycles, therefore this here is a tree. Right? Here I'm looking at the undirected version of this. I could also look at directed versions. Then you have a concept of a directed tree if it has no directed cycles. Okay. So these are all basic definitions. Most of you have seen this in an earlier class, I hope. So now the question is, what kind of graph problems are there and what kind of graph algorithms are in the standard textbook, and how can we use them? So the first graph algorithm that we typically learn is what's called as depth first search and breadth first search. Let me do that one at a time. Thank you. So let's start with depth first search. I'm not going to go through the entire depth first search, but we need to understand what does it take as input and what does it produce as output. So if I draw depth first search as a black box, what is its input and what is its output? Anyone? First of all, what's the input? A graph, right? So this is just a graph with a vertex set and an edge set. Typically, depth first search, you also have a start vertex, right? So S is the start vertex, and it's some vertex from the vertex set. So one of the vertices is identified, and you say, I want to do depth first search from here. And the output is unclear. What is the output? Anyone know?
Traversal order?
Yeah, so it's typically not very clear. The typical goal of depth first search is to visit every vertex and every edge in some systematic manner. So traversal order could be one. This typically gives you a lot of information, but perhaps the right answer should be a depth first search tree. Depth first search tree tells you which vertex was first visited from which other vertex. Okay? So in fact, it's just a simple table that says, here are all the vertices, 1, 2, 3 up to n, and this is the parent of that vertex. Okay, so this will tell you where they came from. Somewhere here is the vertex S, and that would have a parent pointer of nil because there was nothing that was visited prior to it, right? And all others will tell you where it was first visited from. What was the vertex from which you got there for the first time? Of course, depth first search also has some properties. The main property that it has is that the way it goes about is that it starts from the start vertex and then continues as long as it can go. Whenever it can't go anymore, whenever it doesn't find anything new, then it backtracks and continues. So you will find recursive versions of this algorithm written in almost any standard textbook. But you can also find a non-recursive version. So there are two versions of depth first search. One is a recursive and the other is a non-recursive. Okay. And the time complexity of depth first search turns out to be n plus m, where n is the number of vertices in the graph. So n here is the size of the vertex set, and m is the number of edges. So m is the size of E. And by the way, m here is always less than or equal to n choose 2 because we don't allow multi-edges, we don't allow self-loops. So this is the maximum number of edges that are possible if you have n vertices. Is that clear? Okay, so these are things that you need to know. By the way, even though m here can be very large, in fact, it can be as bad as big O of n squared. This here is considered a linear time algorithm. Because it's linear in the number of vertices and the number of edges. So even though the number of edges can be quadratic in the number of vertices, what we know is that the input here must go and and must specify each of the edges. So therefore, the time complexity of depth first search is linear in the size of the input. That's why it's called a linear time algorithm. Okay? So you're going to, in your package, you will certainly need a code for a good working code for depth first search, and you need to make sure that it uses a linear time algorithm just in case. And you also need to know that the input to this graph is provided as the input to this graph is provided in the form of an adjacency list and not in the form of an adjacency matrix. Okay, so that's a little minor detail. If you can check all of that, then this is the first algorithm you're going to need in your package to be ready. The second algorithm that's very closely related is called breadth first search, of course. The input and output are the same. So here also it's graph, and here also it's a tree. We're going to call it a breadth first search tree. And typically, breadth first search is not written as a recursive form, although it's possible to write it. So we're going to assume that it's a non-recursive version, and the time complexity is still n plus m, and therefore this also is linear time. Now, because of the properties of depth first search and breadth first search, one of the main applications of depth first search and breadth first search is to solve what problem? What problem do you solve with? What is the main graph problem that you can solve using depth first search and breadth first search?
The maze problem can be solved with VFS.
Sorry?
The maze problems.
Maze problems. Okay, but is there a broader family of problems that sorry? Dynamic programming.
Shortest path problems.
Shortest path problems. Not quite.
Connectivity?
Connectivity is the answer I'm looking for. Okay. So for both of these, the main application, the fundamental application is connectivity, which is what we wrote down there. So this, anytime you have a problem that asks about connectivity, which says, can you reach this from this? Are these two in some connected piece? Then you should be thinking about depth first search and breadth first search. Is that clear? So basic operation, basic problem to solve using this is connectivity. What else? Once you're done with breadth first search and depth first search, the next level of complexity comes with the problem of minimum spanning trees. So in order to do that, I need a couple more definitions. So let me start with that. Here we talked about what is an example of a tree. We said this is an example of a tree. It turns out that this is also an example of something called a spanning tree. A spanning tree is a tree that connects all the vertices. So in this case, this tree connects all the vertices. And so therefore, this tree is also an example of a spanning tree. Okay. So this here, same example. Now, spanning trees are interesting because they help you to build a network that connects all the vertices. So therefore, there's an interesting problem that comes about related to something called minimum spanning trees. Where should I write this? Let me erase this part here. Sorry. Both of these solve the same problem, where if you're given a graph, let's see. If you're given a graph with a vertex set V and an edge set E, and if you're given something called a weight function, where every edge has an assigned weight. So the way you mathematically write this is that the weight takes every edge and maps it to a real number. Okay? So think of the weight function as a mapping from the edge set to A to the real number line. If you're given a graph with edge weights, then Kruskal's or prims are two algorithms that compute something called the minimum spanning tree. Now, a minimum spanning tree is a spanning tree of minimum weight, where the weight of the spanning tree is simply the sum of the lengths of the edges in the graph in that tree. So this here, we've been given all the edge weights here. So this is 2, this is 3, this is, I never wrote that down. This is 7. I don't have that written down as well. Here's 19, here's 11. Sorry, not 11. Here's 2. 5, 4, and let me say 7 here as well. And then that's it. Okay. So if these are the edge weights, then this particular spanning tree has a total weight of, I have to provide a number here. This is of weight 2 plus 3 plus 5, which is 10, 17, 24, 43, 45, 50, 54. So the total weight of all the edges here is 54. Okay. The spanning tree with the absolute smallest possible weight is called the minimum spanning tree. Now, it's not a unique minimum spanning tree. It's possible that a graph has more than one minimum spanning tree, but they should all have the same weight. So a minimum spanning tree here will produce a spanning tree of minimum possible weight. Now, what are we left with? We're left with figuring out what is the time complexity of these algorithms. So the time complexity, it turns out that there are many different versions of this. In the first version, the amount of time it takes is m log n, and in a second version, the amount of time it takes is m plus n log n. Okay. It turns out that this is the Kruskal's algorithm, or some it's a suboptimal version of the Kruskal's algorithm, whereas this is the best version of the Prim's algorithm. So you can kind of forget this. In most cases, these two will not make too much of a difference for you at the competition level. So you could pick either of these in most cases. There are special cases where you'll find that the Prim's algorithm is actually a little bit faster than Kruskal's. This is Prim's and this is Kruskal's. What the actual algorithm is, we will need time to discuss that. We won't be able to do that now. But it's useful to know what it does. It takes a graph and produces the minimum spanning tree, right? And this is the time complexity. So if you have lots and lots of edges, then the dominant term here, m here, is roughly n squared. If you don't have a lot of edges, the dominant term is n log n, and roughly that's the time complexity. Okay? So this is something that you should know. You should, even if you don't know the precise time complexity, you should know that it's somehow dependent on m and n log n. Okay? Any questions so far? So, Kruskal's algorithm is useful for solving what's called as a minimum spanning tree problem. Now, a minimum spanning tree may not exist. Under what conditions does a minimum spanning tree not exist? If they're not connected. So if the graph is not connected, you're not going to have a tree, you're not going to have a spanning tree, you're not going to have a minimum spanning tree. Okay? So in a way, this also tests for connectivity. Because if it doesn't succeed in finding one, then you know the graph is not connected. However, if I ask you to test connectivity, which algorithm would you use? Would you use this or this? This is the linear time algorithm. This one is not quite linear time. At best, it's an n log n algorithm, even if the number of edges is small. If the number of edges is large, it could be as bad as quadratic. Okay? Of course, this also would be quadratic if the number of edges is large. So really, our interest is in understanding what happens when the number of edges is not quadratic. If the number of edges is not quadratic, this here is linear in n. This is proportional to n log n. Okay? So that's the dominant term. So therefore, this here is going to be slower than this. This is the one to try first. Don't go around thinking about Kruskal's and prims if you can solve it using depth first search or breadth first search. Okay? You can also use depth first search or breadth first search to check whether a graph is a tree. So I'm going to call it tree question mark. If I give you a graph and I ask you, is this graph a tree? Then how would you do that using depth first search? Well, it turns out that there is a simple way to do this. And the simple way is, what do we do?
Check if it's connected and then make sure there's n minus 1 edges.
That's right. So if it's connected, then well, at least you know it could be a tree. But in order to test that there are no cycles, you have to figure out that the number of edges is exactly n minus 1. So a spanning tree has exactly n minus 1 edges. Any spanning tree has n minus 1 edges. Okay? So if this graph does not have exactly n minus 1 edges, then even though it's connected, it's going to fail because that extra edge is going to form a cycle. Okay? So you can use depth first search, breadth first search in order to test whether a graph is a tree. You can also check whether it has a cycle. You're given a graph, and you're asking the question, does it have a cycle? You can do that with this in a similar fashion. All you have to do is to check whether it's connected. If it's connected, you have to check whether it has more than n minus 1 edges. You could still test this even if the graph is not connected. If the graph is not connected, there is a way using depth first search and breadth first search to list all connected components. So you can take the graph, if it's not connected, break it down into connected components, and then all you have to check is whether each of the connected components, whether any of them has a cycle. If even one of them has a cycle, there's a cycle in the graph. Okay, so it's possible that this might need the connected components algorithm if you don't know whether the graph is connected. Is that clear? The connected components algorithm will take a graph, and instead of outputting the DFS tree, it will output all the connected components. Okay. The problem, does it have a cycle? It'll take as input a graph, and it will output yes or no, depending on whether it has a cycle. This here will take a graph and will output yes or no, depending on whether it has the whole graph is a tree. And finally, this here will take the input a graph and decide whether the graph is connected or not. So slightly different problems, but they all can be solved using depth first search and breadth first search. Kruskal's minimum spanning tree algorithm is a little more expensive, so you should use it sparingly. You should use it only when depth first search and breadth first search don't work. And here you solve the minimum spanning tree problem. So it'll take a graph and it'll produce a minimum spanning tree if one exists. Okay.
Excuse me, Professor. I
Yeah.
I don't quite I still don't quite follow. Like for the connected components, when would that be, like, how should I say, like when would that be useful, like to return the connected components?
Right. So I just told you that in order to check whether a graph has a cycle, how do you do this? First, you have to check whether it's connected, right?
Right.
And then, which we know how to check because we know depth first search or breadth first search. And then you have to check that the number of edges is exactly, if it is more than n minus 1.
Oh, right. If it's more than, I guess you need both to be able to tell if, if it has a cycle.
Well, so if it is more than n minus 1, we know immediately that there must be a cycle. However, that doesn't work if it's not connected.
Oh, I see. I guess if you're dealing with something that's
So
not
if it's
connected,
then you have to first list out all the connected components and then do this test on each one of them.
Oh, okay, I follow now, because you could have a graph that's not connected.
Exactly.
You might want to see if it has a cycle.
Exactly. It might be not connected, but still it may have a cycle, and that'll test it.
Oh, that makes sense. Okay.
Yeah? Okay. So again, this is a higher level view where we are not looking at the actual algorithms, but we are trying to figure out which of these modules to use as and when needed. Clear? And we are also understanding the time complexity that are for the algorithms that are involved. Okay, next. So the next set of questions have to do with paths and shortest paths. So until now, we have not talked about paths. We have mostly talked about either connectivity or some properties of these graphs. Now we are going to talk about actual computations. And in these computations, the first set of problems are what are called as shortest path problems. So shortest path problems, there are several different kinds. In the first version, I will give you a start and an end vertex, a source and a destination. And your job, and by the way, I'm going to assume that the graph is weighted, meaning each of the edges has weights. And then I'm going to ask you the question, find me the shortest path from S to T. Okay? So here I'm giving you the start vertex and the end vertex, and your job is to help me find the best path. Of course, you want to take edges that have smaller weight, but you can't just randomly just keep picking the smallest edge all the time. There is a certain way that this whole thing works out. And the algorithm in order to find this is called what algorithm? That's called Dijkstra's algorithm, right? So this is Dijkstra's. Again, you don't need to know what Dijkstra's algorithm is. As long as you have the code for it, as long as you know how to run this program, you can actually work this out. The second set of problems, you're given a source vertex, start vertex, and you're asked the length of the shortest path to every other vertex. Okay, so this is also called the single source shortest path problem. Single source shortest path. Okay, and it turns out that Dijkstra's algorithm also solves this problem. In fact, Dijkstra's algorithm solves this problem, and while you're solving this problem, you get a solution for this as well. Okay?
Oh, you put single source and like shortest path, I guess.
Right. Here you want single source, meaning only the source is fixed, but you want the shortest path to every other vertex.
Oh, I see. Okay.
Okay. And since you're doing it to every other vertex, you also, by the way, have the one to vertex T.
Right.
So this here is an easier version than this, but in reality, Dijkstra solves this version. So this is a bonus that you get. All right. Finally, you have something called the all pair shortest path. We'll do that separately because that requires a different algorithm. Dijkstra's algorithm runs in time. Anyone remember this? My algorithm students, yes? Sorry? 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 Yes? What answer do I hear? Same as prims. Very good. Yeah. So it's actually m plus n log n. Okay. Now how that is achieved is quite complicated. It'll take an entire class to answer that question. But hey, if you have code for it, then you might as well just use it. Okay? So if you have a good implementation of Dijkstra's, it runs in time m plus n log n. It'll find you the shortest path from a single source to every other vertex. Okay? The only thing you need to know here is that the weights are all positive, or at least they're non-negative. Okay? If the weights are not all positive or non-negative, then Dijkstra doesn't really work, or at least it could fail. It's not guaranteed to work if you have negative weight edges. If you have negative weight edges, you have to use a different algorithm. That's called the Bellman-Ford algorithm. That's right. So we have shortest path problems with negative edges. If this happens, then you use something called the Bellman-Ford algorithm. So this thing is a little more general. It allows us to use negative weights in the graph. And the time complexity for this, anyone remember this?
Empty.
Yeah, m times n, yeah. Okay. It turns out that you have to run this n number of times. But you can skimp on the second part, so make it a little more efficient. In the end, you get something like m times n. If you have n squared edges, this is very expensive. Okay, for a dense graph, this is actually quite complicated. And so you have to know that this becomes cubic if the number of edges is large, whereas this guy here is still quadratic if the number of edges is large. So more expensive if you have to deal with negative weights. Okay. And finally, we have one more shortest path problem. This one is called all pair shortest path. And this all pair shortest path uses an algorithm called Floyd-Warshall's. And this guy here has a time complexity of, anyone? N cubed. So it's independent of the number of edges. It's n cubed. Well, actually, it turns out you could say you could also run it in m times n plus n squared log n. So you could run n Dijkstra's algorithm. And if m is very small, this could actually be slightly better. Okay? So time complexity, not so important. But you should know that problems are getting more and more complex. There you have linear time algorithms that deal with connectivity, cycles, and what else? Connected components. Then you have weights. Once you have weights, interesting problem has to do with minimum spanning tree. And there, the best is m plus n log n. So it's, it still has the number of edges to deal with. Then you have shortest path problems. You have single source shortest paths, and you have all pair shortest paths. In single source, the time complexity is the same as your minimum spanning tree algorithms, and it's roughly m plus n log n. And remember, m can be as bad as n squared. So this here is probably quite expensive, but in the best case, you're going to get an n log n time algorithm. Whereas here, if you're dealing with negative edges, then it becomes even more expensive. And if you have to do every pair of vertices, it becomes even more expensive. This is the worst, and it takes n cubed time. So this, if you know this many graph algorithms, and if you have code for them in your package that you're going to go with the competition, you can safely assume that you can try a couple of these graph problems. Now, graph problems, nobody's going to tell you that your input is a graph. Nobody's going to tell you that these are weights. Instead, they'll give you some English language problem where you're in some deep tunnel and you're helping out ants to get to their food or something like this. And your job is to figure out where is the graph here, okay? So modeling the problem as a graph problem is your first challenge. Okay? So many interesting problems are actually very simple problems, but they're actually graph problems. And one of them we actually did, I don't know, did we do it this semester? The one with cleaning the switches going left and right? Yeah. So if you recall, that problem was basically a connectivity problem. And there the problem was that you had to help some guy clean up a shrimp tank. And there were switches that could be turned vertical or horizontal. So the problems are not going to look like graph problems. Forget about it. They won't talk about reachability or connectivity or many of the terms we've talked about. Your job is to figure out how the heck you're going to turn it into a graph problem. Okay? Many of these maze problems you mentioned are really graph problems. So if you do see a maze, then there is a good chance it's really a graph problem, and you can figure this out. There is also another class of problems where they're called implicit graph problems, where the graph may not be explicitly given to you, and you may never have this graph explicitly, but you still have to implement either a depth first search or a shortest path or whatever it is. A typical example is if you want to search on a grid. Let's say you're in Manhattan and your job is to find your favorite restaurant. And you know it's roughly in this direction, but you don't exactly know where. And the question is, how are you going to find it? Maybe you're going to use depth first search, where each vertex is a street corner, and your edges are the streets, right? So you may have to simulate a graph algorithm on some grid like that, where the graph is never explicitly given to you. Maybe it's too expensive to actually explicitly construct the graph, and and you would just simulate this on the fly. Okay, so those are things to watch out for. What else? So this here is just your basic graph algorithms. There are many other way more interesting graph algorithms. So let me mention 2 or 3. How am I doing with time?
4:30.
Yeah? Okay, good. Okay. So I have about 15 minutes. Good. So let me try and talk about some advanced graph problems. Yeah? Everyone have this? Can I erase it? Okay, so the first interesting.
Professor, before you talk about this one, the all pair shortest path. Yeah, the all pair shortest path problem. What that is like you have a pair of vertices and like you're trying to find like the shortest path.
All
like,
pairs. You don't have a pair. All pairs.
But let's say like so between like all pairs, like let's say 1 and 2, 1 and 3. So you basically
Exactly.
find the shortest path.
Correct.
Oh, I see. I guess it would be kind of like if you were Manhattan and you were trying to find the shortest path between 2 places.
No, the way you want to think about this is, do you know what a road atlas is? Have you seen these road atlases that people used to have before they had everything on a cell phone?
Okay, sure.
Did your parents ever have one? There are these road atlases, and in there you would see a table that says Miami to Orlando. And you go and read that and say, it'll say 225 miles. Then it'll say Miami to Atlanta, Miami to Kansas City, Miami to Salt Lake City, Miami to Dallas.
Right.
And depending on the column, you go and read that. That's an all pair shortest path distance table for you.
I see. So it takes all the pairs of, like basically all pairs of vertices in the graph and it finds
That's
the
right.
shortest path that connects all of them.
Well, don't confuse finds from gives you. So I have a table here where I have all the cities listed in, I don't know, alphabetical order.
Okay.
And I have the same set of cities listed in the same order. And if I want to go from this city to that city, I go look it up over here.
Oh, I see.
I want this table as the output. How do I do it?
Oh, I get it. I get it now. Yeah, that's a good analogy.
Okay. So my output here, yeah, it's worthwhile to actually draw this as the, so here again you have a graph and you have weights, and for the all pair shortest path, APSP, right?
Okay.
I want as output a table of distances between any pair of vertices.
Okay.
So I want this table. Actually, this table, as you know, I only need half of it, right?
Right.
Yeah. So I have all the cities here, all the cities here, and the distance between this city and that city is going to be over here.
Right, the shortest distance.
Shortest distance. Good. Yes.
So it would be something like from Miami to Orlando, it's 200 miles.
Right.
Mm.
Okay.
Yeah.
So it's the length of the shortest path that you're going to find in that table.
Ah, yeah.
Okay. Any other questions? All right. So we're talking about the next level of complexity as far as these problems go. So it turns out that the next level is called, I'm going to call them higher connectivity. What does that mean? So it turns out that a graph which is given by a vertex set and an edge set is said to be one connected if I have to remove at least one vertex to disconnect it. Okay. Now we had a tree here somewhere which I erased. It looked something like this. Right? That's what it looked like. In this tree, I can remove any vertex. If I remove this vertex here, what happens? The graph falls apart. It becomes disconnected. Okay? So this graph is called one connected. It is connected, but if I remove one vertex, it falls apart. Okay, so that's the definition of one connected. You can now imagine what is two connected. What's that?
You would have to remove two vertices.
I'd have to remove at least two vertices
To basically break the graph.
to basically break the graph. Yeah.
Or yeah, break or disconnect, yeah.
Now what's an example of a two connected graph?
Square.
Sorry?
A square.
A square, generalize that now. Any cycle. Okay. If I have any cycle, this is a cycle. Can I disconnect it with one vertex removal?
No.
If I remove this vertex here, I can still connect things from the other direction. Right? Forget about the vertex I've removed. That's not something that's going to be connected to anything. It's gone. But the other vertices are still connected. Right? So the graph is not disconnected. If I run depth first search on a vertex on a graph without this vertex, it would still say it's connected. So I would have to remove two vertices in order to break this graph. So this is an example of a two connected graph. Yes?
Does that apply to a cycle where it's just like a triangle?
Sorry? Yeah, that also is a cycle. It's a three cycle. So a triangle is a simple cycle with only 3 edges. What I've drawn here is one with more. He mentioned a square. So this also is a cycle, but it has only 4 vertices. This has more. So any cycle is 2 connected.
But I don't see how, if you remove 2 from the triangle, how it would be disconnected.
I see. So well, that's a degenerate case. It's not worth worrying about. So here you could say, yeah, you need to have. You don't want a trivial solution. Yeah, here if you remove 2, it's still connected. So yeah, it becomes unnecessarily complicated. So if you want, you could say graph is with at least 3 vertices, with at least 4 vertices. And then your definitions will be all right. Okay. So yeah, we won't worry about degenerate cases. So similarly, I could also talk about k-connected, where I have to remove k in order to break some things. What's an example of a 3-connected graph? Anyone? Starts to get a little complicated.
If you just add every edge you can, then it's always reconnected.
A star. So a star is actually 1 connected because I can remove the center of the star and it falls apart. Okay. But you're close because I can add this, and now it's 3 connected. Right? Is that clear? If I remove 1, nothing is going to happen. If I remove 2, nothing is going to happen. It's still connected. If I remove 3, well, I have to remove specific 3. I could remove these 3 guys and it'll fall apart. Clear? So these are great definitions. They're fun-looking problems, but then the algorithms get really nasty. So question is, I give you a graph and I ask you, is this graph 2 connected? Well, first of all, is the graph 1 connected? How do you test this?
Like a vertex should be connected by only one, the lowest.
What's the definition of 1 connected?
At least one we should remove. One vertex we should remove.
Well, you're looking at it the wrong way.
There's no articulation points.
Right. So a graph is 1 connected if it cannot be disconnected with. Well, first of all, if the graph is disconnected, it's not 1 connected, right? So any connected graph is 1 connected. Is that clear? So therefore, in order to test 1 connectivity, all I have to do is to run depth first search or breadth first search. Is that clear? Right?
Sorry, I didn't get it. Why is every connected graph a 1 connected graph?
Because the definition of 1 connected says I have to remove at least 1 vertex in order to disconnect it. Of course, you have to remove something because it's connected to start with, right? So every connected graph is 1 connected. So in order to test whether something is 1 connected, all I have to do is to check for connectivity, which is the same as doing depth first search or breadth first search, right? How do I check whether a graph is 2 connected? This is nastier. Remember, this doesn't mean that any pair of vertices removal will disconnect the graph. That's not what we're saying. We're saying that you have to remove at the least 2 specific vertices in order to break it apart.
Well, here's an idea from what we said, like from what we discussed earlier, we could, you know, like we were saying that it has a cycle, so we could check for cycles.
Well, all I said was that was that this is an example of a two-connected graph, but we don't know.
Oh, I guess we don't know if all two connected graphs have cycles.
Are just yeah, or
You know
they're
how
just
you said a square, and then you said let's generalize it. It has a cycle.
correct, correct, yeah, yeah.
I think if every vertices in the graph is connected to at least two other vertices, then that's a two connected.
Not good enough. I'll show you.
Not to at least, but
Okay, this is here every vertex is connected to at least two others.
oh, right.
Didn't work, right? Is this graph two connected?
No.
Why? Because removing this will disconnect it. Interesting, huh? So this problem gets really interesting, and it's quite complicated, but there's code for something called biconnectivity, which is the same as two connectivity. And I could provide you with code for this, and this is actually worth keeping. So this here is called a articulation point in the literature. And if you can find all the articulation points, or if you can find even one articulation point, then the graph is said to be one connected, not two connected. Because articulation points are vertices whose removal breaks the graph. So you run this algorithm for articulation points, or the biconnectivity algorithm. It will list out all the articulation points. If that list is empty, then you have a two-connected graph. It gets harder for three-connected or k-connected. Okay, so the algorithms there require fancier stuff. We'll talk about that later.
What is the definition for an articulation point?
Articulation point is exactly that. Its removal. Articulation point is a specific vertex whose removal disconnects the graph.
Is there any other way that we can define it?
Yes,
Maybe
there are.
based
There.
on the number of vertices, or
No, it has nothing to do with number of vertices or its neighbors or anything like that. We see here, I can put more of these. So this here will remain an articulation point. Depending, I can put in more of that, and it'll still be an articulation point.
It seems like the common element in all the graphs that you drew is that if we separate all the graphs from the articulation point, they all become separated graphs.
Right,
of the
but that's the definition.
Right, yeah.
Okay.
So in which other way can we define it?
Well, it has other definitions that come from actually depth first search. There's a way to provide it something called a depth first search number and an additional number, and you can define it using those numbers, or you can define it using something called back edges. If the back edges don't go above this point, then it's an articulation point. So there are multiple definitions, but all those come from the algorithms themselves and come from understanding this concept a little bit more.
I was gonna say it's kind of like what you said. I mean, yeah, I was gonna say something like a way to look at it is kind of like what you said. It's a point that connects everything. That's how you can look at it.
Yeah, but it's a little dangerous to think that way. So, for instance, this might look like this is an articulation point.
Right.
However, I could mess with you and add an extra thing here. So what I've done is I've created two of these points now, right?
Yeah.
And they both have similar properties. They both connect to all these things, right?
Right. Yeah.
So now
yes.
is this two connected or not?
Oh, I see. I guess so. What the question is, if you remove those 2 points, like, is it so? If you remove those 2 points, like, would it disconnect it?
I'm asking, is this an articulation point?
Based
Okay,
on what
right
we
now
said,
I
no.
like I don't know. Right now I feel like it is.
You said what?
Based on what we define the articulation point, I mean, like the
Yes or no?
line definition.
Yes or no?
No.
Say no. Why?
Well,
Because now you have this other thing to go through. Okay, so it gets complicated. I can give you more examples, but we're running out of time. I want to spend 2 minutes on another class of problems. So connectivity is a fabulous place where you have lots and lots of interesting problems. Another class of problems are what are called as flow problems, network flow. In network flow, you assume that your graph corresponds to some kind of a pipeline. The oil pipeline in Texas or Alaska or wherever the heck they have oil is often made into a network. Here, each of these edges have a direction, and they typically go from an oil well to, I don't know, some kind of oil storage thingy, or maybe a port. Okay, and they send it through pipelines. There may be multiple oil wells from which things are going, and they all end up in some storage place. Okay, but each of these pipes have capacities, have limits. So here you have a capacity that says whatever 10 10,000 gallons per minute or whatever their capacities might be. So each of these has a capacity, and you're asked how much oil can I send from here to there, given all the capacities of these edges. These are called network flow problems. Again, even if you don't know how this works, even if you've never heard of this problem, you should go and find code for network flow and take it with you for the competition, because these are very, very important problems. And they're nasty because there's a lot of variations of this problem, and secondly, there are many, many problems that you can easily and quickly turn it into a network flow problem. Okay. So they don't look like anything we've seen so far because it doesn't have to do with shortest paths. It doesn't have to do with any of these other things. You're just asking how much oil can I send from here to here, maximum, given all the capacities of all the links. Not at all easy. In some cases, it turns out that you have to reduce the flow on a certain pipe in order to increase the flow from one end to the other. Problems get quite complex, quite interesting, but this is a good place to stop. Okay?
I guess when you